So, our next speaker is Debanjana Kundu from CRM, and she will talk about control theorems for fine Selmer groups.
Thank you. Whatever I say today will be joint work with Meng-Fai Lim. I will be talking about control theorems for fine Selmer groups. So for those who don't think about Iwasawa theory every day, or for those of you who don't really know what is Iwasawa theory, I just want to briefly tell you about what we study. So it started in the 1950s with the work of Kenkichi Iwasawa, and classically, the goal was to study growth questions. So growth questions essentially of class groups. And the key idea was that you wanted to study the class group or the size of the class group for a particular number field, but that was a hard question. So Iwasawa noticed that if you could put them in p-adic analytic towers, then their growth properties would stabilize, and then you could do some sort of a descent and get information that you initially wanted to get. And the other object that we know and love from number theory or arithmetic geometry are abelian varieties, or if you don't want to think about abelian varieties, you can just think about elliptic curves. And an important question is to study rational points on these objects. And one of the only ways of doing so is by studying the size of the Selmer group. And there is this broad philosophy that Selmer groups and class groups somehow have similar properties. So Mazur in 1972 made use of this notion and studied the growth of Selmer groups in p-adic analytic towers. So he introduced what's called the Iwasawa theory of Selmer groups of abelian varieties. But what he noticed was that even though the class group growth that was studied by Iwasawa was sort of similar to the Selmer group growth of abelian varieties, but there were some very, very key differences. And I don't want to get into the details of it, but what was realized around 30 years after Mazur's paper was that there is a subgroup of the Selmer group called the fine Selmer group that has properties closer to that of the class group. And it is there are reasons to believe that this fine Selmer group, which I will define in the next few slides, is interpolating the growth of class groups and Selmer groups in p-adic analytic towers. So this will be our main object of study today. So what are Selmer groups? So Selmer groups basically are objects. So there's a technical definition here, but just to say it in words, this measures some sort of local global failure. And this is over a base field or a number field F, but to see what's happening at the infinite layer, you can just take direct limits. And so the fine Selmer group, as I mentioned, is a subgroup of the Selmer. And how do you define it? You're just putting more conditions of vanishing at primes above P. So again, the technical definition is not so important for the purpose of today's talk, but so this is something smaller than the Selmer, and there are more vanishing conditions at primes above P. But again, you can take direct limits and study what's happening, not at just the number field at F, but as you go up to it, as you go up the tower. Now, my title also said control theorem. So what are control theorems? Now, Mazur, in that 1972 paper, he realized that there's this natural restriction map going from the Selmer group. So maybe I shouldn't say, whenever I say Selmer or fine Selmer, I really mean like the P primary Selmer or P primary fine Selmer. So he noticed that the restriction map from Selmer of the elliptic curve over F to the G invariance over the infinite extension, this map is not an isomorphism. So there is a kernel and a co-kernel, and he really wanted to study how much do these two objects differ. And that is the control problem. And there was this remarkable result that he proved. He said, if you're looking at a ZP extension, so your Galva group of L over F is the group of p-adic integers. That is a p-adic analytic extension. And your elliptic curve has good ordinary reduction at primes above P, then the kernel and co-kernel of the restriction map S on the previous slide, they're both finite and bounded as you vary over all finite extensions inside the script L. So this was the first result towards, this was the first control theorem that had been proven. And a very interesting corollary of that theorem is that you can actually show how does the Shafirevich-Tate group grow as you go up the tower. So if you assume the finiteness of Shaw for a number field, there's this precise growth formula that you can give. So these constants lambda and mu are non-negative, and mu is, so these are non-negative integers, and mu can be any integer. So if you go high up enough in a tower, this is telling you exactly what the size of the Shafirevich-Tate group is. Now, Greenberg in 2003 generalized the result of Mazur, and he said, you don't have to just look at ZP extensions. You can look at essentially any p-adic Lie extension that arises in number theory. So there is some technical terms that I've written here. I've written it for those who probably have seen this theorem before, but it's not really important for today's talk, the technicalities. But so the conditions are essentially, they show up everywhere in number theory, the very natural conditions. And he again studied the kernel and the co-kernel of the restriction map. And he was able to show that in general, the kernel and co-kernel are finite. He was not able to prove boundedness. In fact, he showed that it is possible that as you vary over all finite extensions inside script L, the co-kernel can be unbounded. And the kernel and the co-kernel can be unbounded. And maybe just to give you some examples where his theorems hold are, again, you don't have to just look at ZP extensions. These can be any multiple ZP extensions, ZPD extensions, or any p-adic Lie extension where the inertia subgroup has finite index in the Galva group. And there's, again, another, what might look slightly technical, but again, it's a very naturally arising condition for towers that arise from geometry, so to say. But you have lots of examples where Greenberg's theorem holds. Now there's an analogous control problem for fine Selmer groups. So it's the same problem. You sort of know that this fine Selmer group and this G invariance of the fine Selmer group over the infinite extension, this map is not going to be an isomorphism. So you want to understand the kernel and the co-kernel. And what were results known in this direction? So in Rubin's Euler systems, that orange book, so that book was published in 2000. So that's why I've given 2000 with a question mark, because I don't know if this result was published anywhere else. He was able to prove some results in the direction of a control theorem for fine Selmer groups. So what did he say? He said, you take any abelian p-adic Lie extension, so it's a ZPD extension where D can be bigger than or equal to 1. And he insists that primes above P and the primes of bad reduction of E are finitely decomposed in the tower. So he does not want your primes to say split completely, or even, yeah, split completely. And then he's able to say that the kernel and the co-kernel are finite. And what I should mention is that, in fact, there are lots of ZP extensions, not just ZPD extensions, but lots of ZP extensions where it is known that this condition does not hold. So his result was not for all ZPD extensions. So this is, so these are, there are examples where this condition does not hold. But still, you should keep in mind that this result is independent of the reduction type at P. So there is no ordinary assumption, unlike in the control theorem of Mazur and Greenberg. And in 2004, Wuthrich, in his PhD thesis, actually was able to show that for ZP extensions, when D, that is when D is precisely equal to 1, the kernel and the co-kernel of the restriction map is finite and bounded for all ZP extensions. So for all ZP extensions, you have a statement just like Mazur's control theorem, but even stronger because you do not have any restriction on the primes above P being good ordinary. So what are the sort of results that Mengfei, Lim, and myself we prove? So firstly, we prove a very general control theorem for fine Selmer groups. So there is no restriction on the sort of the ZP extension, the sort of the p-adic analytic extension. And there's also no restriction on the reduction type. But since it's a very, very general result, it's not very strong. And so we very quickly just try to understand what's happening in special cases, or cases that are essentially the ones that we tend to be more interested in. So we are able to improve upon the general result of Rubin. So again, we get rid of the hypothesis that he had about on finite decomposition for multiple ZP extensions. We are able to study what happens in certain non-abelian extensions, like the false state extensions and also trivializing extensions. So these are extensions which are obtained by attaching to your base field the P power division points of the elliptic curve. And we're not only able to say that the kernel and co-kernel are finite, but we're also able to give a bound on their growth. And this also allows us to actually study the asymptotic growth formula for the fine Selmer group itself as you go up the tower. And I must point out that when I showed the preprint to Antonio a couple of weeks ago, he pointed out to us that this should be provable. So we did that recently. So I just want to quickly give you a flavor of the sort of results we prove. So the first one is we are not looking at the case D equals 1 because that has already been studied. So we look at the case D bigger than or equal to 2, and we get an explicit bound on what is the kernel and what's the co-kernel. And I have a star over here just because, as I will point out on the next slide, that if you have some additional information about what the growth or what the tower is like, you can actually do better for the co-kernel growth. I must also mention that we would probably expect that it might be possible to actually improve this to showing that the kernel is infinite and bounded. So it's a big O of 1, because there is no dependence on D. And yeah, so but the proof that goes through for D equals 1 that Wuthrich had, unfortunately doesn't go through in this case, but maybe it is possible to improve this bound. And in terms of the asymptotic growth, so the fine Selmer group itself might not be finite, just like the Selmer group need not be finite over a number field, but you can still get a formula for what the torsion part looks like. And so yes, there is a mu invariant. This is called a generalized mu invariant. It's essentially just a constant if you go high up enough in the tower. And what I would want to point out is that this growth, so we have a big O of n p to the d minus 1n, and that is really coming from the fact, that's not coming from the error term of the kernel or the co-kernel, because our error terms here were big O of n and big O of p to the d minus 1n, but it's coming from results essentially due to Cuoco and Monsky, where they were studying the asymptotic growth of the highlighted guy, and that has this big O of n p to the d minus 1n. And so in order to do better, we would have to work on Cuoco-Monsky's result, which seems to be very hard. And also, unfortunately, it is not possible to get an asymptotic growth formula for the fine analog of the Shafrevich-Tate group, despite us having a pretty explicit asymptotic formula for the fine Selmer group. And that's because the fine analog of the model way that shows up is not well behaved. Okay, so now talking about the trivializing extensions. So the theory of complex multiplication actually tells us that if E is an elliptic curve with CM, then your Galba group F infinity over F, so you've attached all the P powered division points, so that's F infinity, and that extension is a dimension 2 abelian extension, so that's a ZP2 extension. So our previous results should tell us that the co-kernel is a big O of P to the 2 minus 1, that's just 1 times n. So, but because we have more information on what this extension is like, we can actually give a better bound in this case.
So there's a question in the chat.
Yeah.
They ask what is Fn? Is Fn the fixed field of G to the P to the N, or is it something else?
Yes, absolutely. I'm sorry about that. Yeah. And right. So, and yes, if you further know that P is a prime of potential ordinary reduction, then you can actually also show that the kernel is finite and bounded. So you can do a little better because you have more information about the structure of the extension. And in the non-CM case, so this is a dimension 4 non-abelian extension. And so once again, you can show that the kernel has the same big O of n growth, which becomes a finite and bounded growth when you have potential reduction, potential ordinary reduction. And the co-kernel growth is of this form, and the 2 is essentially a 4 minus 2, the 4 coming from the dimension. So like over here, you had a big O of n and no power of p because it was a 2 minus 2. And so over here, you have a 4 minus 2. So that sort of gives the bound. So I did not write down my false Tate extension results because I was not sure if I would have time to explain what a false Tate extension is. But in the last maybe 1 minute that I have, I want to briefly tell you how do we prove these sort of results. So the idea really goes back to Greenberg, and you study a diagram like this. So I've just essentially rewritten the definitions of defined Selmer group and written them with the restriction maps Rn, Hn, and Gn. And the whole idea is to use inflation restriction to understand the kernel of Hn and the co-kernel of Hn, and also the kernel of Gn, which then using a snake lemma argument will give you information about the kernel of Rn and co-kernel of Rn. That's what we were interested in. And maybe I should point out that the most difficult part of this computation is really calculating the local kernel at primes above P. And maybe I'm also out of time, so I should stop here, but I will be happy to take questions.